Welcome back to Sparsh. Starting today, I'm launching a new series where we break down exactly how to tackle coding questions in real-time interview situations. I'll try to post 2 videos over the weekend from now on. Let's jump right into the first problem, which is destroying asteroids. So here you can see that we are given a planet of mass, which is denoted by variable mass itself, and we are also given an array of asteroids. Where each asteroid I represent the mass of the ith asteroid. So we can arrange the so this setting is clear. So we are given one planet and some of the asteroids. Now we can arrange these asteroids in some order where if a planet of size mass m, mass of the planet is greater than or equal to the mass of asteroid. So if mass of the planet is greater than or equal to the mass of asteroid, then the asteroid will be destroyed, which is this, and the planet gains the mass of the asteroid. So the planet can destroy basically these asteroids, and after destroying the asteroids, the planet will also gain the mass of these asteroids. Otherwise, if an asteroid is bigger than the planet, then the planet will get destroyed. So the expectation from this problem is that we need to return true if the planet will be able to destroy all of the asteroids, or if the asteroid will be able to destroy the planets. So let's jump into the example 1. So let's say we are given an asteroid of we are given a planet of mass 10. So let's say this is a planet which has mass 10, and now we also have different asteroids which have mass 3, 9, 19, 5, 21. So this mass 10 can easily take on the asteroids which are having mass 3 or 9 or 5, but it cannot take on right now 19 or 21. So what we can do is we can just pick up the first asteroid, which is mass 10 planet, picking up asteroid of mass 3, then our planet will become of mass 13. Similarly, now 13 will pick up 9. So after picking up 9, the mass of our planet now becomes 22. In a similar fashion, we can now also pick up 19 also, which we earlier was not able to pick up. So if we will take 19, then our planet mass will become 41, and 41 can anyhow pick up 5, and hence our mass will become 46, and 46 can also pick up 21 now. So ultimately the mass of the planet will become 67, and hence here we see that the asteroid, the planet is able to destroy all of the asteroids, and hence we will be returning true here. Now let's go to example number 2, where we basically see that the mass of the planet is initially given to us as 5. So this planet has mass 5, and now the asteroids given to us are 4, 9, 23 and 4. So let's pick up the planet asteroid 4. So our planet size mass will become basically 5 plus 4, which is 9. 9 can also pick up an asteroid of size 9, and hence the planet mass will become 18. Now 18 is not able to pick up 23, but it can definitely pick up 4. So let's pick up 4 for now, and the planet mass will now become 22. So now 22 can obviously not pick up 23, and hence we can say that the planet of mass 5 with this combination of asteroids is not able to pick up, destroy all of the asteroids, and hence we will be returning false. Now let's go to the constraint of the problem. So right now the constraint which are offered to us is that the planet mass can range from 1 to 10 raised to 5, that is manageable in int, as well as the asteroid length. So the total number of asteroid which we are getting, that also we say that the length is given to us as 10 raised to 5, and total number of asteroid mass, like whatever mass is present inside this array, this 49, 20, 24, this can range from 1 till 10 raised to 5. So constraints are also clear. So let's say if we want to implement the solution of this array, then we know that we can consider any algorithm which takes time complexity less than n log n. Now the most intuitive solution which comes to our mind is that let's just sort the array and then just check if the planet mass, currently planet mass after destroying the asteroid X, is greater than next asteroid or not. If we are able to traverse through the whole array, then we can say that yes, we are able to destroy all the asteroids with a planet of mass m, and hence the solution is pretty simple. We got the asteroid array, we have the initial mass of the planet, and then we just sort the array. After sorting the array, we just see that okay, if the planet mass is greater than or equal to the asteroid size, if planet mass is greater than or equal to asteroid size, we know that the asteroid will get destroyed, and hence we will add the planet mass into the asteroid. But as soon as we'll get that the planet is not able to destroy a particular asteroid, then we know that all the asteroids which are further after that asteroid those asteroids are bigger than this one, and hence the planet won't be able to destroy additional ones. We'll just return false. And if let's say planet is able to destroy all of the asteroids, then we'll just simply return true, and hence we'll solve the solution, we'll arrive as the answer. Now here what do you see? The sorting takes n log n time complexity, and this loop obviously takes O of n. So the total time complexity which we received is O of n log n. And space, here you see that we only have taken planet mass and nothing else, and hence space complexity is O of 1. This was time complexity. Now you might be wondering that why have we taken long for mass instead of taking the mass variable itself. So if we go back to the constraints, you can see that the planet has size mass which can range till 10 raised to 5. Let's take extreme situation where the planet mass is given as 10 raised to 5 and all the asteroids are also given. That means that we are given an array which have size 10 raised to 5 itself, and each asteroid inside it is also 10 raised to 5. So what it will do, we are going to add up 10 raised to 5 times. So that means 10 raised to 10, which is out of bound for int. So in C++, we cannot store 10 raised to 10 inside, and hence we need long variable here. So now a very simple, straightforward optimization which we can think of here is, we can if we are sorting the array initially, we know that the asteroid dot end, the last element in the array, if the planet size is greater than the last element in the array, we can say for sure that okay, if we are able to destroy all of the asteroids till now and last element of the array we also can destroy, we can just break through this loop and we can simply return true. And second case is, let's say if the planet mass increases greater than 1e5, greater than or equal to 1e5, which is basically the maximum mass that asteroid can have. So now we know that there can't be any other asteroid which have a mass greater than 1e5, and hence we can again break in that case, and hence we'll return true. Now as an interviewer they can say you that okay, like you are doing everything in time complexity of O of n log n, and space you are using O of 1. So now as space is getting like increasing day by day and spaces are really cheaper, but compute is what is actually costly and is time consuming, and we, let's say this is a production based system and you don't want your user to be waiting, so can we decrease the time complexity from n log n to some other value, and space complexity can be increased. So in that case what we can do is, you folks must have heard about counting sort. So what we can do is we can create a counting sort array, like we can create an array in which we'll just be storing the masses of the asteroid. So let's say asteroid of mass 1, asteroid of, like we can say the index represents the mass 1, 2, 3, 4, 5, 6 dot dot dot, and the basically the value represent how many asteroid exist for that mass. Let's say if we have asteroid of mass 4, then instead of using 0 we'll increase this to 1. If we, let's say, have 2 asteroids of mass 4, instead of keeping this as 1 we'll keep it as 2 now. Similarly, let's say if we have asteroid of mass 6, we'll make it this index 1. So now we are having a counting sort approach array which is having the length 1e5 plus 1. Why plus 1? Because we don't have any asteroid with mass 0, and we want to just use this as simple, like we want to keep the asteroid in the same mass column. Let's say asteroid of mass 1 is stored in position 1, and asteroid of mass 2 is stored in position 2, and so on. And we are also trying to do another optimization in the same approach. We are also keeping a min element and max element. So these two variables, what they will track is, they'll track the minimum asteroid size and the maximum asteroid size and max asteroid size. Now I'll just tell you why are we even using these. So first of all, we inserted all the elements in counting sort, how I shown you at the top, that why are we inserting this, and then we are also trying to gather what is the minimum element and what is the maximum element. So what this optimization will help us do is that we already know the minimum element. So let's say you don't have any asteroid which is of size 1000 till mass 1000, you don't have any asteroid. So what you are going to do here is you are going to traverse from 0 to 1000 just to skip those values, and you will get to know that okay, there is no asteroid present in these values. So you basically skip those parts which is behind the main element. Let's say this is main element here. So all the values which you might need to traverse due to counting sort approach, you have skipped them. And let's say this is max element. So you know that all the values lies between these values only, min and max. So all the values afterwards, which is max element till 1e5, you are also going to skip those. And hence this is a very small optimization, but yeah, we can use that optimization. And we also have added the optimization from before, where if planet mass is anyhow greater than 1e5 or planet mass is greater than the maximum element for now, we'll just break the loop and we'll just return true. And similarly, we'll see that okay, whenever the value at counting sort, like if we are seeing that okay, 7 has value 0, so we see that the mass of like a planet having mass 7 is 0. Basically there are no asteroid present which have mass 7. Then we'll just skip and the loop will start again. And we'll see that okay, planet mass is greater than equal to I, because you know that the index is now denoting the masses. We are just going to add that mass into the planet mass, and as there can be multiple asteroids with the same mass, what we are doing is we are multiplying I with its value. So basically this is mass, and this counting sort approach I is basically how many asteroids. So how many asteroids into mass is the total mass which a planet can destroy. And if a planet mass is less than the I, which is planet mass is less than asteroid mass at any given point in time, we'll just simply return false. And hence here what did we achieve? If you'll see that this counting sort approach will take space complexity of On. This for loop is going from I to asteroid size. So basically O of n, and min element can be 1 and max element can be 1e5. So this we can say 1e5 is a constant. So we can say O of k, which is a fixed time complexity. So now from O of n log n, which we are using before, we are now to time complexity of O of k. And but we have compromised here on space. So earlier we were using O of 1 space, but now we are using O of k space again. So here you can see that k space is record for this counting sort approach. O of n we can take it as O of k, and from min element to max element, that is 0 to 1e5, that is also O of k. So you can even, like, instead of writing it to O of k, because the array size can increase, you can even note it as O of n. So from n log n we have reduced to O of n time complexity, and from space complexity we have increased a bit. Yeah, but if the interviewer is asking you to specifically optimize on the time part, we can easily do that. That is all from my side. See you later.